Welcome to identity break number 2. This video really doubles as an introduction to a new function, as well as introducing its identities and properties. But I don't anticipate that it'll take long to do either, so I'll be putting both into this video. The function that I'm introducing here is called arc_base_p. And what it does is measure the arc length of the unit Squircle starting at the angle 0. Here's a visualization of arc of the angle theta. I currently have two ways of defining this function, both which are straightforward from calculus. The first is the parametric arc length formula. We take the 2 norm of the derivative of the vector cos base p and sine base p of t, and integrate it from 0 to the angle theta to get the arc length of the Squircle from 0 to theta. The second way is simply using the polar coordinate arc length formula, which uses hype, since r equals hype base b of theta gives a unit Squircle. Now that we've defined arc, we can go over some of its identities. First, arc is an odd function. This fact comes from how we defined arc. When it comes to even and odd functions, they always switch parity when integrated or differentiated. The function in the integrand here is an even function, meaning its antiderivative will be odd. Next, arc base p is linear with integers at pi over 4. We'll take this one piece by piece. We can see from the 8-fold symmetry of Squircles that this arc length is equal to this arc length, which is equal all over the Squircle. From that, we can deduce that if we wanted to find arc of pi over 2, it would be the same as 2 of arc pi over 4s. If we wanted to find arc of 5 pi over 4, it would simply be 5 of arc pi over 4s. So for any integer multiple of pi over 4, this holds. Using this information, it's easy to demonstrate that arc base p satisfies the general form of linearity, but only for integer multiples of pi over 4. Next is the complementary angle identity, which says that the arc of any integer multiple of pi over 2 minus an angle alpha, when added to the arc of alpha, is the same as the arc of that integer multiple of pi over 2. This is also something that can be shown using a Squircle symmetry. Let's just take the first quadrant, visualizing the arc of an angle alpha. The arc length that would complete the first quadrant is the same as the length starting at 0 and going to the complement of alpha. It follows that the sum of these individual arc lengths would be arc of pi over 2. Demonstrating the cases for any multiple of pi over 2 follows a similar idea to this. Another way of thinking about this identity is if alpha was negated, which, using the parity of arc, then changes the statement to adding the angle alpha to multiples of pi over 2. You can see if we start with arc of pi over 2 and try to add the arc of angle theta, it's the same as tacking alpha's arc length onto pi over 2. Essentially, completing a quadrant is like starting at 0 again when measuring arc length. Finally, arc is a monotonic function, which means it either strictly increases or decreases as the variable increases. In this case, it's obvious that it would be strictly increasing because a Squircle's arc length only increases as we increase the angle. A consequence of arc being both odd and monotonic means that it's also invertible. So there does exist some mysterious inverse arc function, but I have not found an expression for it. And that's it. Here's everything we went through in this video. Arc is odd, linear with integers at pi over 4, works nicely with complementary angles, is monotonic, and invertible. We're gonna really stretch this function out in future videos, so I wanted to get this out of the way before the fun began. Okay, bye!